Hello all. We are Team Lunar Emissary, Team 1 from Sparkman High School. This is our wonderful project lead, Dominic, our chief engineer, Chris, our design lead, I'm Austin, design member, Preston, and outreach lead, Amani.
Today we'll be presenting to you our Family Night presentation for Team Lunar Emissary. This is our team logo, which was designed specifically to show our team identity through each individual aspect. So we have Earth, so we remember where we came from, no matter how far we get in this project. We have 6 astronauts for 6 team members. We have the lunar lander, so that way we always remember how we got here, all the trials, struggles, everything that brought us to where we are today. And then we also have our name, Lunar Emissary. And emissary means messenger, basically. So we are basically the lunar messengers. And as messengers, we are sending the message that we can find solutions today to solve the problems of tomorrow, which is our team slogan. This is the FORCE mission, also known as the Furthering Observation of Research Cratered Environments. And there will be 2 lunar landers and 1 orbiter. The first lunar lander will be called Luke, and the second, Leia. Luke will go to Aristarchus crater, which is the place that we plan to be going, and it will operate for 12 months. And Leia will go to Shackleton crater, which it will also operate for 12 months. Vader is an orbiter that will last for about 24 total months.
So our science objective chosen was, can we produce oxygen in Aristarchus via ilmenite? Oxygen is a material on the moon that has oxygen as a part of ilmenite has oxygen in it. So if we heat it up a lot, then it can release one of its oxygens.
Okay, this is our science traceability matrix. As we said, our science objective is oxygen production via ilmenite. You can see we have our measurement objective, measurement requirements, and instruments selected for this objective. And our instrument requirements, the instruments we'll be using are the inertial measurement unit, or the IMU, the thermocouples, and the LiDAR. And you can see their respective mass, power, data rate, dimensions, lifetime, frequency, and duration. And then this is set up like the last slide. These are our support equipment requirements. The support equipments that we will have are the onboard computer, transmitter, receiver, antenna, and battery. And on this you can see their mass, power, data rate, dimensions, and their other technical specifications. And this is like a part 2 of that slide. You see all the same information for our other support equipments, which are the direct drive servo motor, which is like our wheels, and our motor for the wheels all in one, and then our mini electric piston and the mini rotary motor.
Payload design requirements. Our constraints, it must be roughly the dimensions of a medium-sized carry-on suitcase, a weight limit of 13 one-year-old gators, or 10 kilograms, must survive the external environment, and no harm must be done to any NASA-designed vehicle. The functional requirements it must deploy, take measurements, efficient in power, collect data, send data, and house the payload. Payload destination. Our payload is going near Aristarchus, where it is recorded with high concentrations of ilmenite. The environment ranges from really cold to really hot. The gravity is constant at a 1.62 meters a second squared, 60 microsieverts of radiation per hour, solar winds, and micrometeoroids.
So this is our initial design for our payload, Gator and Bayou. Gator was designed to pull Bayou out of the lunar lander and collect the ilmenite that would be deposited into it so that it could start the process of heating it. And Bayou would be where the ilmenite was heated and hopefully where we would get oxygen. This is the concept of operations. They would start inside the lunar lander and wait shortly before lunar day. Then they would exit, and Gator would detach and get the ilmenite, deposit it into Bayou, and then Bayou would start the process of heating it. This is our concept selection trade study. This is not what it's supposed to look like, but this gator and bayou won over our other concept, which we did not show, cow. A few categories that tipped it in gator's favor was science objective and likelihood of project requirement. In the end, we chose a bit of both. We combined the wheels or rover idea from gator, the lens from bayou, and the claw from the cow. So this will kind of make it more compact and easier to obtain the requirements of size and weight. Our concept of operations is similar to gator and bayous, where it initially starts in the lander, and then shortly before lunar day, it will roll out of it, collect samples, and then finally come to rest and start heating the ilmenite.
Okay, this is our material selection trade study. All of the figures of merit were provided to us by UAH. The three different materials that we came up with that we wanted to use for our hull were grade 5 titanium, aluminum alloy 7075, and I-220H beryllium. The one we decided to use was the beryllium, mainly because it was everything we were looking for. It was light, it was durable, it could withstand the temperatures and radiations that it would endure on the moon. And you can see the density and durability were the two factors that it won in on the trade study.
This is our final design, pod, the payload for oxygen derivation. It is also the name for a group of baby alligators, the more you know. This allows for a better, lighter, compact design. It still uses the lens. And it has been designed to incorporate the best of all our designs.
And this is our requirements compliance. This is just saying that we are within compliance of all of the requirements that were given to us by UAH, which were the mass and volume, the survivability, and all of the functions that it would have to do in our mission. And this is our risk analysis. The risks that we came up with were not obtaining enough ilmenite, overheating, tipping over, the arm being broken, and not enough time before night. And then you can see on the right a visual aid that shows the risks, different impacts, and their relative likelihood.
And now we'll move on to our outreach summary.
So for our first phase, it was at Sparkman High School. We assisted Lockheed Martin in a balloon tower competition, and it showed that it was basically to showcase teamwork within the people who were competing. And for our second ACE, it was Sparkman High School Expo Night, where we practiced our presentation skills and we just showcased our team as a whole. And this is our third ACE, where we went to Legacy Elementary. We did a Diet Coke and Mentos experiment with the kids to showcase rocket propulsion to connect it back to our InSPIRESS project. And for our fourth ACE, which is here right now, it's right now basically. And then for our fifth ACE, we plan to go to Legacy Elementary tomorrow for Moonlight, where we'll display a model of our payload, basically doing the same thing we're doing here today. And these are our Instagram analytics. We have over 7,000 views and 490 interactions within our Instagram, and these are our posts that we have so far.
In summary, we designed Pod, which is made to collect ilmenite and heat it up to try and extract oxygen. We believe that Pod is great for our mission or for NASA's mission, because it can collect oxygen. And if we can get oxygen from natural minerals on the moon, it'll be huge for them in making a moon base in the future. And we got 5 total ACEs, 5 outreach platforms, including a billboard, and we have 4 that need to be updated. but lots of views over all of our outreach platforms. Thank you.